Assalamualaikum and salam sejahtera. So class, in this lecture we continue to the chapter number 8, which is about Boolean Algebra. Basically, this chapter is closely related with the first chapter, which is discussing about the foundation of logic and proof. Alright, so Boolean Algebra provides the operations and also the rules for working with the set that contains binary digits, which are 0 and 1. Alright, so Boolean Algebra provides operations and also the rules for working with these two numbers, 0 and 1. The three operations in Boolean Algebra that will be used are, the first one is complementation operation. The second operation is Boolean sum, and the third operation is Boolean product. Okay, we start with the complement operation. The complement operation, okay, the complement of an element denoted by bar. Okay, we have 0, so this is the bar notation. This is 1, so this is the bar notation. Alright, so denoted by a bar is defined by, for the complement of 0 is equal to 1 and the complement of 1 is equal to 0. Okay, so for the Boolean sum, so Boolean sum is a binary operation. That means it requires two inputs, okay, and produce single output. So Boolean sum denoted by this sign, okay, addition sign, or also by OR, has the following values. For 1 plus 1, it is equal to 1. 1 plus 0 equal to 1. 0 plus 1 equal to 1. And the only value that gives 0 is when the outputs are equal to 0 and 0. 0 plus 0 equal to 0, while the other additions equal to 1. As long as the digit 1 appears, so the outcome equal to 1. Alright, so for finish with Boolean sum, we move to Boolean product. So for Boolean product operation, it is denoted by single dot. Okay, it is called, okay, like this, single dot, black dot. Alright, or also by n, has the following values. For 1 times 1, it is equal to 1, otherwise it is equal to 0. Okay, it requires both inputs equal to 1 in order to get output 1, otherwise the output equal to 0. 1 times 0 equal to 0, 0 times 1 equal to 0, and 0 times 0 also equal to 0. Alright, so the rules of precedence, that means the priority for Boolean operators, okay, is arranged as the following. The highest priority is parenthesis. Okay, the highest priority is parenthesis, and then followed by complements, and then the third one is Boolean product, and the last one is Boolean sums. Alright, so in mathematics, as usual, parenthesis almost our highest priority. So same goes with Boolean operations. Alright, in Boolean operations, so if you have parenthesis, our highest priority is parenthesis. Okay, and then followed by complements, and then product, and also the last one is sum. Alright, so consider the first example. Find the value of 1 times 0 plus, in parentheses we have 0 plus 1 and complement. Alright, so in this problem, okay, we have parentheses, we also have a complement operation, we have a Boolean sum, and also we have Boolean product. So according to the previous slide, we have to answer this question based on the precedence or the priority. Okay, since there is a parenthesis, the highest priority is parenthesis. So we solve the problem inside the parenthesis first. Alright, and then followed by complement. After complement, so we need to solve the product, and the final one is the sum, Boolean sum. Alright, so how to answer this question? We start with the parenthesis. So 0 plus 1 is equal to 1. Alright, so after parenthesis is complement, so 1 complement equal to 0. Alright, so after complement, the next one is product. So 1 times 0 equal to 0. So the last one is Boolean sum, so 0 plus 0 equal to 0. So that's the answer for this question. The second problem. Okay, the second problem, we have two parentheses. We have complement, we have Boolean product, and also we have Boolean sum. So we start with the parentheses. Since we have two parentheses, so we solve both parentheses. So in the first parenthesis, we have 1 complement. So 1 complement is equal to 0. Okay, 1 complement is equal to 0. And in the second parenthesis, we have 0 times 1. 0 times 1 is equal to 0. Okay, so finish with the parenthesis. Okay, the first two parentheses. Now, in the next step, we have another parenthesis, 0 plus 1. So we solve this one. 0 plus 1 is equal to 1. And then we have complement. 0 complement equal to 1. So next is the Boolean product operation. So 1 times 1 equal to 1. So that's the answer for this problem. The next problem doesn't have any parentheses. So after parentheses, the highest priority is complement. So we solve all the complement first. 1 complement equal to 0. And then we have 0 complement equal to 1. 0 complement again equal to 1. And then we solve the Boolean sum. Okay, this one, 1 times 1 equal to 1. 1 times 1 equal to 1. And finally, we solve the Boolean sum. Okay, 0 plus 1 plus 1, because 1 is appear there. So the final answer is equal to 1. Alright. The following are corresponding to each other. As I mentioned before, this chapter is closely related with the first chapter. Okay, so we have corresponding relation here. Complement corresponds. Complement operation correspond to the logical operator. Okay, this one, this operator is a negation operator, right? From the first chapter, it is negation. So complement is correspond to the negation logical operator. So Boolean sum correspond to the logical operator disjunction operation. Okay, and then for Boolean product, it is correspond to the conjunction operator. All right, and for 0, it is correspond to capital F, which is stand for false, and 1 is it is corresponds to T, capital T, which is representing the true value. All right. Okay, so equalities, just this notation in Boolean algebra, can be directly translated into equivalence. We have these triple horizontal lines representing equivalence relation, all right, of compound propositions. So conversely, equivalence of compound proposition, equivalence is denoted like this again, can also be translated into equalities in Boolean algebra. So I'll give you an example. Translate 1 times 0 plus, in parentheses, 0 plus 1, and then we have this one, okay, complement, into a logical equivalence. So this is the solution. A logical equivalence can be obtained by translating each one into capital T, which is stand for true. Each 0 into capital F, which is stand for false. Each Boolean sum into disjunction, this notation, and each Boolean product into a conjunction, this notation. And each complementation, okay, the bar sign into a negation sign. Okay, we change every operators to the corresponding logical operators. All right. So this is the solution. Thus, we have 1 times 0 plus 1 complement is translated into, we have capital T, okay, and then we have a conjunction F, because 1 is equal to T, this one equal to capital F. All right, so this one is conjunction, this one is disjunction. Again, in parentheses, we put the same parenthesis, but outside the parenthesis, if here we have complement operator, so here we have the negation operator. 0 we replace with 0 with false, true with 1 with true, because this is addition operation, so it's same. Okay, 0 plus 1 equal to 1 plus 0, also the same. So we have T, we have a conjunction here, sorry, disjunction, and then we have F. All right, so previously we showed that the value for this Boolean expression is equal to 0. So because equation can be, it is correspond to congruence. So in here, we replace the equation with congruence, because it is equal to 0, so we have congruent false. Okay, because 0 is equivalent, is correspond to false, capital F. Alright, so in the next example, the question asks you to translate the logical equivalence into Boolean algebra, okay, into Boolean identity. Alright, so the question, translate the logical equivalence conjunction T, disjunction, we have negation here F, and the equivalence here T, alright, into an identity in Boolean algebra. So we do the reverse process. Okay, we do the reverse process. So capital T, it is equivalent with 1. This one is equivalent with Boolean product. So this one is equivalent with 1. So this one is equivalent with Boolean sum. Alright, so negation is equivalent with complement. So we have F, that means 0, complement. So the congruence, it is equivalent with equation. So T, we have 1. Alright, so this is the solution. Okay, thus the translation of this expression is this expression. Okay. Okay, now we consider this definition. Let B be a set contains 0 and 1, and then B to the power of n is a set. It is a set contains n tuples. N tuples mean we have n entries here. Start with x1 up to xn. Okay, again the order is meta. So we have x1, x2 up to xn. There are n entries. Okay, where xi, each xi belongs to the set B. That means xi either 0 or 1. Because in the set B, it contains 0 and 1 only. For all I equal to 1 up to n. So B to the power of n is the set. It is a set, okay, of all possible n tuples. N possible n tuples of 0 and 1. Okay. I give you example. Let's say our n is equal to 3. Okay, so our B3 is equal to a set contains 3 tuples. Because n equal to 3, so we have 3 tuples. It contains all possible 3 tuples. We start with x1, x2, and x3. Okay, 3 tuples where xi belongs to the set B. That means it is either 0 or 1 for all I in the closed interval 0 and 3. Okay. Okay, so this is 3 tuples. So all possible n tuples. That means all possible n tuples, we might have 1, 1, 1, 1, 0, 1. What else? 1, 1, 0, 1, 0, 0. Okay, all the possible combinations of 0 and 1 in the form of 3 tuples. Alright, all the way up to until 0, 0, 0. Okay, all the possible combinations of 0 and 1 in the form of 3 tuples. Alright, so that is set for B3. The variable x is called a Boolean variable. So this is our Boolean variable. We have 3 here for case n equal to 3. If it assumes value only from B, it is only 0 or 1. Alright, that is, if its only possible value are 0 and 1, a function from this set to this set, from Bn to B, is called a Boolean function of degree n. Okay, we're referring to the value of n representing the degree of the function. This is the example. So the Boolean function f with input x and y is equal to x times y complement. Okay, it is actually f x y equal to x y complement. Okay, from the set of ordered pairs of Boolean variables to the set 0, 1 is a Boolean function. So this is our Boolean function. Okay, of degree 2. Okay, because we have two variables, so of degree 2 with f11 equal to 0, f11, f10 equal to 1, f01 equal to 0, and f00 equal to 1. Why it is equal f11 equal to 0? Okay, f11 means our x equal to 1, our y equal to 1. And the function is x times y complement. So if x equal to 1, 1 times 1 complement, okay, it is equal to 1 times 0. 1 times 0 is equal to 0. Okay, how about f10? f10 means our x equal to 1, our y equal to 0. So x times y complement, it is equal to 1 times 0 complement. So 1 times 0 complement equal to 1. So 1 times 1 equal to 1. So if we list down all the output for f11, f10, f01, and f00, so we can come out with the table 1. Okay, table 1. This is all the possible combinations, and this is the output for each combination. Boolean functions can be represented using expressions. Made up from variables and Boolean operations, like given in the previous function. Okay, it made up from expression. Sorry, it is using expression made up from variables x and y, and also Boolean operations. We have x, we have Boolean product, and then we also have complement on y. The Boolean expression in the variables x1, x2 up to xn are defined recursively as a and b. Okay, we have 0, 1, x1 up to xn are Boolean expressions. If e1 and e2 are Boolean expressions, then the complement of the Boolean expression e1, okay, is also a Boolean expression. The Boolean product of these two expressions, e1 and e2, also is a Boolean expression, and Boolean sum of these two expressions also another Boolean expression. So Boolean expressions can produce another Boolean expressions using the Boolean operators. Each Boolean expression represents a Boolean function. The value of this function are obtained by substituting 0 and 1 for the variables in the expression. So let's consider this example. Find the value of the Boolean function. Okay, our task is to find the values of the Boolean functions represented by the following function. So we have three inputs, x, y, and z. The function is x times y plus z complement. All right, we have three inputs, x, y, and z. That means we need to list down all the possible arrangement for this, possible inputs for these three inputs. Okay, as given in this table. Okay, in the first three columns, we list down all the possible distinct arrangement for these three inputs. We have 1, 1, 1, 1, 1, 0, 1, 0, 1, all the possible arrangement for these three inputs without any repetition. Okay, without any repetition means every combinations is unique combination. And then we consider the output for each combination. For example, we start with this column. We start one by one. Okay, because in the function we have x times y and also z complement, so we need to have these columns as well. Okay, we have x times y, also we have z complement. So we start with x plus y, so we have x times, 1 times 1, it is equal to 1, 1 times 1 equal to 1, 1 times 0, it is equal to 0, 1 times 0 equal to 0, 0 times 1 equal to 0, 0 times 1 also equal to 0, 0 times 0 equal to 0, 0 times 0 equal to 0. And then for the z complement, we are referring to the column z. 1 complement equal to 0, 0 complement equal to 1, 1 complement equal to 0, until the last one, 0 complement equal to 1. And finally, we consider this operation. We have Boolean sum. So 1 plus 0 equal to 1, 1 plus 1 equal to 1, 0 plus 0 equal to 0, 0 plus 1 equal to 1, 0 plus 0, 0 equal to 0, 0 plus 1 equal to 1, 0 plus 0 equal to 0, and 0 plus 1 equal to 1. So this is the value for the given function. We move to the next one, which is about Boolean identities. So identities of Boolean algebra are particularly useful in simplifying the design of circuits. Okay, it's very useful to make your circuit simpler, okay, than the original form. Okay, we have the table 5 for the Boolean identities. So the complement of x complement get original x. Okay, that is the law of double complement. X plus x again equal to x times x also equal to x, so comes from the idempotent laws. X plus 0 equal to x, 1 times x plus 1, x times 1 equal to x, comes from the identity law. X plus 1 equal to 1, x times 0 equal to 0, comes from the dominant law. And x plus y equal to y plus x times y equal to y times x, comes from commutative law. Alright. So we also have another table for the remaining identities. Okay, you can find these identities easily from the book text. Alright. Another example. Show that the distributive law, okay, from the previous table is valid. Okay, is valid. That means, what does it mean? It's valid. So we need to show that the left hand side is equal to right hand side. Okay, so one of the ways to solve this problem is using the table. All right, using table. So the first step is to come up with these three columns, x, y, and z, because we have x, y, and z. That means we have three inputs. Okay, and then list down all the possible combination of these three inputs. Okay, unique combination. There is no repetition. Okay, and then come out with each column. We have y plus z here, so we have this column. We have x plus y, so I have this column. We have x times z, we have this column, and then combine together we have this one, x times y plus z, and we have x plus y plus x times y plus x times z. So the given law is valid when these two columns are identical. Okay, so after you come up with all these possible combinations and then try to come up with the output. Okay, for example, x plus z, we have 1 plus 1 equal to 1, 1 plus 0 equal to 1, and so on until the last one. All right, and then x times y, so x1 times 1 equal to 1, 1 times 1 equal to 1, and so on until the last output. Alright, for xz, we consider this column, x and z, so 1 times 1 equal to 1, 1 times 0 equal to 0, and so on until the last one. Alright, and then we move to the next one. We have to multiply using the Boolean products x times x plus z. That means we multiply this column number 1, and we multiply with column number 4. Okay, 1 times 1 equal to 1, 1 times 1 again equal to 1, and so on until the last output. Alright, and then for the last column, we consider xy. This column number 5, and also this one, column number 6. Okay, 1 plus 1 equal to 1, 1 plus 0 again equal to 1, 0 plus 1 equal to 1 until the last output. So clearly, both columns, this column and this column, are identical. Okay, same 1 1 1 1 1 1, and all the remaining values equal to 0. So this we can conclude that the given distribution law is valid. Okay, so this is another example. Translate the distributive law, okay, this law, into a logical equivalence. So let's see how to solve this problem. The steps are, the first step is to change the Boolean variables. Here we have x, y, and z, so we change to p, q, and r respectively. That means x equal to p, y equal to q, and z equal to r. Alright. Next, change each Boolean sum into disjunction. Into disjunction, and each Boolean product into conjunction. Okay, the transforms of the Boolean identity, the given identity, into the logical equivalence after we do all the changes, so we can come up with this expression. Don't forget to change from equation to equivalence notation. All right, so that's the complete answer for this example. Alright, the next topic is about duality. The concept of a dual can be used to explain the relationship between two identities. Okay, previously we have Boolean identities. So to explain the relationship between two identities in form of pair, so we can use the concept of duality. The dual of a Boolean expression is obtained by two ways. The first way is to interchange between Boolean sum and Boolean product. Means if we have Boolean sum, so we change become Boolean sum, so we change becomes Boolean product. Okay, if we have 0, so we interchange becomes 1. Okay, that's duality. Okay, for example, find the duals. Find the duals of these two expressions. First, we have x times y plus 0 and x complement times 1 plus y in parentheses y complement plus z. Okay, we interchange one by one. Alright, we interchange one by one. Interchange the Boolean product sign and the Boolean sum sign. Okay, so in here, the parenthesis means Boolean product. Okay, the parenthesis means Boolean product. So Boolean product, it becomes Boolean sum. Okay, and then in parenthesis we have Boolean sum. So we change becomes Boolean product. Okay, and then we have x. Okay, we have y, maintain with y. Okay, so 0 interchange with 1. Don't forget to put again the parenthesis. That's for the first one. For the second one, x complement. Okay, we keep it as maintain with x complement. So Boolean product interchange with Boolean sum. So 1 interchange becomes 0. Boolean sum becomes Boolean product. Okay, y complement we maintain with y complement. Boolean sum becomes Boolean product, and we have z. Okay, and then don't forget to put parenthesis, so Boolean product can becomes parenthesis. Alright, so this one also parenthesis. Alright, so that's the solution for this problem. The dual of a Boolean function represented by capital F represented by a Boolean expression is the function represented by the dual of this expression. This dual function denoted by f to the power of d, d means dual, okay, does not depend on the particular Boolean expression used to represent f. An identity between functions represented by Boolean expressions remain valid when the duals of both sides of the identity are taken. Okay, next is the abstract definition of Boolean algebra. So what is actually Boolean algebra? So this is the definition of Boolean algebra. A Boolean algebra is a set B. It is a set B with two binary operations. So we have two binary operations. Binary operations means the operation that requires two input. Okay, we have Boolean, this one, the disjunction and also conjunction. So both operations requires two input. Okay, this input, this input. This one also same, this input, this input. Okay, so a set B with two binary operations, elements 0 and 1, and a unary operation bar complement. Unary operation bar means it requires only single input. Okay, 1 complement, 0 complement, single input. That's why we call it as unary operation. This one binary operation, this two binary operation, this one is unary operation, such that these properties hold for all x, y, and z in B. So all these properties are valid, okay, or also called as hold. So we have identity law, we have a complement law, associative law, commutative law, distributive law. So you can get all this list from any discrete mathematics books, okay, when discussing about Boolean algebra. Identity law, complement law, associative law, commutative law, and also distributive law. Alright, next is representing Boolean functions. There are two important problems in Boolean algebra. The first problem, given the values of a Boolean function. Okay, so the problem is how can a Boolean expression can represent this function be found? Okay, given the values of a Boolean function, the problem is how a Boolean expression can be represented. Okay, macam mana? How? That's the first question. The second question, is there a smaller set? Is there a smaller set of operators that can be used to represent all Boolean functions? So how to answer these two questions? For the first question can be solved by showing that any Boolean function can be represented by a Boolean sum of Boolean products. Boolean sums of Boolean products of the variables and their complements. That's the way how to answer the first problem. Okay, how can a Boolean expression can represent this function be found? So the answer is, this problem can be solved by showing that any Boolean function can be represented by a Boolean sum of Boolean products of the variables and their complements. So let us show you example to make it clear. So how about the second one? Okay, so the solution of the first problem, okay, shows that every Boolean function can be represented using three Boolean operators. We have Boolean product, Boolean sum, and also the complement notation operation. Okay, for the second problem can be answered by showing that all Boolean functions can be represented using only one operator. All Boolean functions can be represented using only one operator. Previously, using both three operators. So for the second question, only one operator. Both of these problems have practical importance in circuit design. That's why it is important. Okay, give you example. Find Boolean expressions that represent the function f with three inputs x, y, and z, and also function g also with three inputs x, y, and z, which are given in the following table. Okay, so this table, in this question, you are given two functions without any expression. We do not know what is the expression for each function, but we are provided the output for each function according to the inputs. Okay, for each input, we have the output. Okay, we are given the output. So the task now is to come out with the expression f, x, y, and z. What is the expression until we get exactly the same output? The same goes with g. X, y, and z input. What is the expression for this function in order to get exactly the same output? So in this kind of problem, our interest is going to the output with value 1. So we have this one. Okay, we also have this one, also we have this one, and then refer to the corresponding input. Okay, that means for x equal to 1, y equal to 0, z equal to 1, the output for f is equal to 1. Okay, and then for input x equal to 1, y equal to 1, and z equal to 0, the output for the g equal to 1. And also for the input x equal to 0, y equal to 1, and z equal to 0, the output for the g is equal to 1. Okay, let's see how to solve this problem. An expression that has value 1 when x equal to 1, z equal to 1, and y equal to 0. So first we solve for the function f. Okay, for the function f, the output for the f equal to 1 when x and z equal to 1 and y equal to 0. Okay, it is equal to 1 and the value 0 otherwise. For all other combinations, the value for the f equal to 0. 0 otherwise is needed to represent f. Such an expression can be formed by taking the Boolean product of x, y, complement, and z. Boolean product means when x, okay, says x times y complement and z. Okay, so when all this value equal to 1, then the output equal to 1. So how this one can hold? It is hold when x and z equal to 1 and y equal to 0, because 0 complement equal to 1. Alright, so again 1. Okay, so finish with f, we move to g. G has two inputs with G has two outputs with value 1. To represent G, we need an expression that equal 1 when x and y equal to 1 and z equal to 0. That's the first combination. Or, this is the second one, x equal to z, which is equal to 0, and y equal to 1. Also give you the output equal to 1. So we can form an expression with these values by taking the Boolean sum of two different Boolean products. Okay, two Boolean products, we put addition at the middle. Okay, sum of two different Boolean products. The Boolean products x, y, z complement has the value 1 if and only if x equal to y equal to 1 and z equal to 0. Similarly, the product of x complement times y times z complement also has the value 1 if and only if x equal to z equal to 0 and y equal to 1. Okay, it is equal to 1 when x equal to 0 means 0 complement equal to 1 times y equal to 1. Okay, times again 0 complement equal to 1. So 1 times 1 times 1, it is equal to 1. The Boolean sum of these two products, this one and this one, represent G. Okay, represent G because it has the value 1. If and only if the only condition that can make it 1 is when x equal to y equal to 1 and z equal to 0, or the two situations x equal to z equal to 0 and y equal to 1. Okay, so this example actually illustrates a procedure for constructing a Boolean expression. Constructing a Boolean expression representing a function with given values, like given in the previous table. You're only given the table, the values, and also the function f and g without the actual expression for each function. Each combinations of values of the variables for which the function has value 1 leads to a Boolean product of the variables of their complements. So, as I mentioned before, our interest goes to the output with equal to 1. Okay, to come up with the expression for each function. Okay, so we have another definition. This time it's about two terms, literal and min-term. A literal is a Boolean variable or its complement. Okay, a literal is representing to a Boolean variable or its complement. A min-term of the Boolean variables x1, x2 up to xn is a Boolean product. So min-term is a product. Okay, so literal is a Boolean variable. Min-term is Boolean product of y1 times y2 times up to times yn, where yi equal to xi or yi equal to x complement. Okay, where yi equal to xi or yi equal to x complement. Suppose our I equal to 3, for example. So we have y3 is equal to x3 or y3 equal to x3 complement. Either one. Hence, a minterm is a product of n literals. So actually, a minterm is a product of n literals with one literal for each variable. A minterm has the value 1 for one and only one combination. For one and only one combination of values of its variables. One and only one combination of values of its variables. More precisely, the minterms, this is the minterms, y1 times y2 times up to times yn is equal to 1. The value is equal to 1 if and only if yi equal to 1. Yi means each element in minterm, yi is 1, and this occur if and only if xi equal to 1. Okay, when y1 equal to xi, sorry, yi equal to xi and xi equal to 0 complement, sorry, xi equal to 0, and when yi equal to xi complement. Okay, because 0 complement, it is again equal to 1. Another example, find a minterm. Find a minterm that equals 1 if x1 equal to x3 equal to 0, and we have x2 equal to x4 equal to x5 equal to 1, and equals 0 otherwise. Okay, other than these values, the value for the minterm equal to 0. So this is the solution. So we have 1 complement times x2 times x3 complement times x4 times x5. So let's see what is the answer. So we have x1 equal to 0, so 0 complement times y2 equal to 1 times x3 equal to 0, so 0 complement, x4 equal to 1 times 1, so we have 0 complement equal to 1 times again 1 times 1 times 1, and also the final answer, because this is the product of the value equal to 1, so we have 1. So that's the answer. Has correct set values. By taking Boolean sums of the distinct minterms, taking Boolean sum of distinct minterms, minterms plus minterms plus minterm. Okay, so from this sum we can build up a Boolean expressions. Okay, combinations of several distinct minterms we combine by using Boolean sum operation, so we can come out with another Boolean expression with a specified set of values. In particular, a Boolean sum of minterms has the value 1. Okay, we add all the minterms together. So this new expression has the value 1 when exactly one of the minterms in the sum has the value 1. So it has the value 0 for all other combinations of value of the variables. That means otherwise, it come out with the value 0. So consequently, given a Boolean function, okay, a Boolean sum of minterms can be formed that has the value 1 when this Boolean functions has the value 1. We highlight this one and also this one. And has the value 0 when the function has the value 0. Okay, given a Boolean function, a Boolean sum of minterms, as I mentioned before, we can add together several distinct minterms by using the Boolean sum operation. So we have Boolean sum of minterms. So these sums can be formed that has the value 1 when this Boolean and function has the value 1, and has the value 0 when the function, the given function, has the value 0. The minterms in this Boolean sum correspond to those combination of values for which the function has the value 1. So the sum of minterms, okay, sum of minterms, some distinct minterms, we add together by using the Boolean sum operations. Okay, it represents the function that is called with special name. We call this function as sum of product expansion. Sum of product. Okay, product comes from the minterm because minterm is using the Boolean product operation. So we add together, that means it is sum. Sum of product expansions or also can be known as disjunctive normal form. Disjunctive normal form. Alright, of the Boolean function. So I give you example. Find the sum of product. Find the sum of products expansion for the given function f, x, y, and z equal to x plus y times z complement. So this is a function with three inputs, x, y, and z. The sum of product. The sum, this is our task to find the sum of products. Sum of products expansion of the given function can be found in two ways. Okay, give you the first way. In the first way, we use Boolean identities as given in the previous table. Okay, Boolean identities to expand the product and simplify the expression. Okay, as given in the following steps. So we have the given function, x plus y in parentheses, and the outside parentheses we have z complement. So using distributive law, we can expand this expression becomes x. Okay, you multiply 1 by 1, so we have x times z complement plus y times z complement using this distributive law again. And then in the next step, using identity law, okay, x actually we can times 1z, it is equal to again to x z complement. Same goes with here, 1 times y z complement, it is equal to this one. That's why we call it as identity. Okay, so from here, the element 1 can be substituted by using this parenthesis. We have y plus y complement because it is equal to 1. This one also, we have 1 here, so we have this parenthesis. X plus y complement, x plus x complement, it is also equal to 1. Okay, this one equal to 1. This one also equal to 1. So this law is come from unit property. And then we expand, okay, x we bring to the inside parenthesis, z complement also we bring inside the parenthesis. So we have this expression. We have x, y, z complement plus x, y complement, z complement. Same goes with this one. We bring this one inside the parenthesis. So we have x, y, z complement plus x complement, y, z complement. So this is come from the distributive law. We make it, we simplify this expression. We come out with the last one by using the idempotent law. All right. So this is the sum of term. Okay, we have this one product, another product, three product. We combine together by using Boolean sum. Okay, so this is the first way. Another way to get the sum of product expansion is by using table. The second way is to construct the sum of product expansion by determining the values of the function for all possible value of variables x, y, and z. Okay, first of all, we come up with these three default columns, x, y, and z, and all the possible combinations of these three variables. Okay, and then we put inside the expression, we have x plus y, and then multiply with z complement. We have z complement. Okay, and then this is the output. So we consider all outputs equal to 1, equal to 1, equal to 1, and our interest goes to this side. Okay, so the sum of products expansion of f is the Boolean sum of three minterms corresponding to three rows of this table that give the value 1 for the function. Okay, we start with this one, x, y, and z. Okay, so x, y, and z complement. Okay, we have x, y, and z complement. This is for the first one. For the second one, we have x, y complement, z complement. Okay, we have x, y complement, z complement. Okay, and the third one, okay, the second one and the third one, we have x complement, y, z complement. So we have x complement, y, z complement. So we obtain all the interns in, and then that's the expression. Okay, the minterms and the whole expressions. All right. So it is also possible to find a Boolean expression that represent a Boolean function by taking a Boolean product of Boolean sums. So previously we have Boolean sums of Boolean product. So this is the reverse way. We have a Boolean product of Boolean sums. So this kind of relation, we have special name also. The resulting expansion is called conjunctive normal form. Conjunctive normal form. Previously we have disjunctive normal form. So this time if we use Boolean product of Boolean sums, so it is called conjunctive normal form, or also known as product of sums expansion. Product of sums expansion of the function. Okay, we move to the next topic, which is about logic gates. The basic element of circuits are called gates. Okay, we have gates. Each type of gate implements a Boolean operations. Each type of gate implements a Boolean operation. So in Boolean operations, we have three. Okay, we have bar, which is the conjunction. Complement. We also have a Boolean sum and then Boolean product. Okay. Okay, combinational circuits can be constructed. Okay, can be constructed using three types of element. The first element is called inverter. Okay, it's called inverter, which accepts the value of one Boolean variable. So that means it accepts single input, either 0 or 1. Okay, single input, only one value. One Boolean variable as input and produces the complement of this value as its output. Okay, so this gate, okay, this inverter, it receives single input and produce single output. Okay, single input, single output, and it produce the complement of the input. Okay, if the input is 1, so the output is 0. If the input is 0, so the output is 1, the complement value. So this is the symbol that we use to represent the inverter. Okay, we have the input X, single input. We have arrow here, that means the direction is to this side. So this triangle, and we have small circle. Okay, in the exam, make sure you provide the correct symbol. We have triangle, we have circle, and also we have arrow. From which direction to which direction, it is important. Okay, you need to provide the complete symbol for the inverter. Okay, we have single input and single output, and the output is the complement of the given input. Okay, if the input is 1, so the output is 1 complement, which is equal to 0. If the input is 0, so the output is 0 complement, which is equal to 1. So that's inverter. The input to the inverter is shown to the left side, this side, entering the element, this one, and output is shown to the right side, this one, leaving the elements. The next type of element that we use, okay, after inverter, we have OR gate. OR gate. These inputs, okay, the inputs to this gate are the values of 2 or more. Alright, so the input can be greater than or equal to 2. Not necessarily only 2, it can be 2, 3, and so on. Alright, it can be multiple input for this kind of gate. The output is Boolean sum. Okay, so if we have xy, so the output is x plus y. If we have three inputs, x, y, and z, so the output is x plus y plus z. for the OR gate. The operation is Boolean sum. Okay, it can have more than two inputs. So the output is Boolean sum of their values. So this is the symbol. Okay, it is almost like D but not D. Okay, we have curly here, and also we have this one. Okay, make sure you write or you draw the symbol properly, especially in your exam. All right, that's the way how to draw the symbol for the OR gate. The inputs to the OR gate are shown to the left side and the outputs to the right side. Okay. The third type of the elements we use is the AND gate. AND gate, so the inputs to the gates are also, it can be two or more inputs. Okay, X, Y, Z, and so on. Alright, Boolean variable. So the output is the Boolean product. So the operation is Boolean product. Okay, if the input is X and Y, so the output is X times Y. If we have another one, Z, so the output is XY. Sorry. XY, Z. Because the operation is Boolean product. So this is the symbol for the AND gate. We have capital D. Without any curve. Here we use straight line. And we have just like capital D. Alright. So we have two inputs and single output. Multiple inputs to AND or OR gates are permitted. As I mentioned before, it can be more than or equal to two inputs. The inputs to each of these gates are shown in the left side entering the element, and the output is shown on the right side. Okay, so example for multiple input. Okay, we have x1, x2, x3. Because this is an AND gate, so the output is the Boolean product of x1, x2 up to xn. Okay, don't forget to put this triple dot to indicate that we have n inputs. If you have only 3 inputs, so no need to put this triple dot. But if we have n inputs, so we need to use this triple dots to indicate there are some elements at the middle. Okay. So same goes with the OR gate. Okay, we have 3 n inputs, x1 up to xn, so we have triple dots. Okay, and the operation is Boolean sum. Okay, combinations of gates. So we can combine together all these gates and come up with a circuit. Combinational circuits can be constructed using a combination of inverters, OR gates, and AND gates. When combinations of circuit are formed, some gates may share inputs. Okay. This is shown in one of two ways in depiction of circuits. So one method is to use branching. Okay, I'll show you later how to use the branching. That indicates all the gates that use a given input. Different gates but using the same input. You can use the branching. The other method is to indicate this input separately for each gate. I show you here the example. So in here, okay, we list down all the inputs separately like this. Okay, another way is using the branching. So this is the branching. We have two different gates here using the same input xy, so we have this branching, black dot, and then use this sign, okay, to indicate. That means we it is not connected with this line. Okay, that means this line is not connected with this line. Okay, it's passed through from above this line. We use this sign. Okay, so it goes here, same goes with this one, black dot goes here. That means these two gates using the same inputs. So this is the branching method. For this one, we just use normally, list down all the inputs normally. No need to use branch. Okay, this one is for branching method. Alright, so in these two figures, as you can see, we combine all the gates together. We have inverter here, we have AND gate here, we have OR gate here. Okay, we have multiple inputs, multiple gates, but produce single output. Okay, single output. Okay, for example, here we have x and y goes to the AND gate, so it becomes x times y. Here x, it goes to inverter, it becomes x complement. Y, it comes in original form, goes to the AND gate, so it becomes x complement y. And then these two inputs goes into another gate, which is the OR gate. Okay, so that's why we have x plus y plus, because it is a Boolean sum, x bar y. Okay. Example, construct circuits of that produce the following outputs. Okay, your task is to construct the circuit using the three gates and or and also inverter until you come up with all these outputs. All these are the outputs is given here, so this is the output. So your task is to come up with this circuit. Okay, for the first one, we have how many inputs? We have x and y. Okay, so we have x, y. So for the first one, it is the OR gate. Okay, so we have this OR gate. So the arrow is pointing here inside the OR gate. So the output is x plus y. And then we need to multiply with x complement. Okay, so we have two ways. The first way is to come out with another input, which is x. Okay, x goes to inverter, so it becomes x bar. Another way is to use the branching. If you use branching, no need to use this one. You just need to put black dot, goes here and draw like this, goes to this side and goes to this inverter. Okay, so no need to draw this one, just use the single x if you want to use branching method. Okay, so the outcome for this inverter is x complement, and then moves to the final gate is the AND gate, because this one multiply with x complement. So x plus y multiply with y with x complement, it is the AND gate. And then this is the output. Don't forget to draw this arrow. Okay, don't forget to put this arrow. That means it is the output for the circuit. The next one, we have x complement times in parenthesis y times z complement, and then again we have complement. Okay, how to answer this problem? So again, we refer to the involved variables. This time we have x, y, and z, because these variables will determine the inputs for the circuit. So we have x, y, and z, so we come out with the original without any complement. Okay, we have x, y, and z. Okay, the original variable. And then we start with x complement, so it goes to inverter, we have x complement. Next is in parenthesis. Okay, we have x plus z complement, sorry, y plus z complement. So y in original form goes to OR gate, but for the z we need to use the inverter operator first to convert from z becomes z complement. Okay, so it goes to the OR gate, so it becomes y plus z complement. Next is the complement for the x plus z complement. So for both expressions we put the inverter, so it is applicable to both elements. So inverter for x plus z complement becomes x plus z complement. And finally we combine together these two expressions using Boolean product, so we have the AND gate. Okay, so this is the output. Don't forget again to write or to draw this arrow to indicate that is your output. Next, okay, again here we have three variables as the input, x, y, and z, so provide in the original form. Okay, and then in parentheses we have x plus y plus z, so we have three inputs to this single gate or gate, so it produces x plus y plus z. And then for these three complements, we have x complement, y complement, and z complement. That means we need to use two separate inverters, because on each inverter can only receive single input. That's why we need to use single inverter for single input. So it receives single input, produce single output. So we have x complement, y complement, and y complement. So these three multiple inputs can goes to the single gate, which is the OR gate. Okay, sorry, the AND gate, because x times y times z, x bar, x complement times y complement times z complement. And the final one is the Boolean product operator to combine these two expressions together. So we use single operator, which is the AND gate. So we combine together. So finally, this is the output. Okay, so I give you one example of application problem. A committee of 3 individuals decides issues for an organization. Each individual votes either yes or no for each proposal that arises. Each individual. Okay, 3 individuals. So let's say we have A, B, and C individuals. And each individual can vote either yes or no. Yes or no. Yes or no. For each proposal that arises. A proposal is passed if it receives at least 2 yes votes. Okay, that the proposal is considered passed if it receives at least 2 yes votes. Okay, from these 3 persons, it received at least 2. Okay, so the question is design a circuit that determines whether a proposal pass. So this is the solution. Let x1 is the first individual votes for yes. Okay, sorry, instead of use A, B, C, we can use X, Y, and Z also. Okay, X, Y, and Z. So X equal to 1 if say yes, and equal to 0 if, okay, X equal to 0 if the X says no. Y equal to 1 if yes, Y equal to 0 if he says no. Z equal to 1 if yes, and equal to 0 if Z says no. Alright. Then a circuit must be designed that produces the output 1 from the inputs X, Y, and Z when 2 or more, because it said at least 2 yeses. Okay, so that means greater than or equal to yes. Then it is pass. Of x, y, and z are equal to 1. One representation of the Boolean function that has 3 outputs values is x plus y, x times y plus x times z plus y times z. So this is the expression that can represent this situation. Okay, so after you come out with the Boolean expression, so the next task is to draw the circuit. Okay, is to draw the circuit. So we have the expression, and then the next task is to draw the circuit. So how many inputs? We have 3. 1 x, y, and z. How many operations? We have Boolean sum and also Boolean products. Is there any inverter required? No, there is no required because there is no complement. So we have plus n, we have AND gate and OR gate. Okay, so this is the circuit for the previous problems. Right, so for that kind of problem, come out with the expression first and then finally provide the circuit. Okay, the final topic is about adders. So logic circuits can be used to carry out addition of 2 positive integers. Okay, 2 positive integers. So we have, let's say, a and b. There are 2 positive integers, so we can use circuit to carry out addition of a and b. So to do this addition, circuitry is built from some component circuits. First, a circuit that can be used to find x plus y. Again, instead of use a and b, you also can use x and y. X and y, suppose they are positive integers. Okay, so we have to find the addition of these 2 integers, x and y, where x and y are 2 bits. The input to the circuit will be x and y. Of course, x and y, okay? Two inputs because these each have the value 0 or value 1. The output will consist of 2 bits, okay? 2 bits denoted by S and C. The first bit is S, the second bit is C. So is stand for some bits, okay? Some bit. And C is for carry bit. So 2 bits, we have S for some bit, and we have C for carry bit. This circuit is called a multiple output circuit because it has more than one output. Okay, because we have outputs in 2 bits. Okay, because the outputs are S and C, so this is we call as multiple output. Okay, previously we have single output. The design circuit is called half adder. Half adder. Why? Because it adds 2 bits, okay, 2 bits x and y without considering a carry from a previous addition. Okay, we do the addition directly without considering any carry bit from previous addition. Okay, so that's why we call it as half adder. Without considering a carry, see, okay, from a previous addition. The input and output for the half adder in table 3, okay, give in the table 3 input and output. This one is input and this with the output. Okay, for the input, because we have 2 inputs x and y, so we list down all the possible combination of x and y. We have 1 1, 1 0, 0 1, and 0 0. Okay, from table 3 we see that c equal to xy. Why? Because xy, when 1 1 1 times 1, it is equal to 1. That's why c is equal to xy. Okay, when 1 times 1, it is equal to 1 and 0 otherwise. Okay, and s, for s, the expression is like this. For example, when x equal to 1, y equal to 1 complement plus x complement x equal to 1 complement y equal to 1. So the output is 1 times 0 plus 0 times 1, it is equal to 0 plus 0, it is equal to 0. You can get this value. So we can do the same process to get all the remaining values. So this is the expression for the S. Okay, for the sum bit. Also, this form also can be transformed by using the Boolean identities, become this expression. Okay, same. Because these two expressions can give us the same output. 0 1 1 0. If you represent, find the value for this one also, you can get the same value, 0 1 1 0. Hence, the circuit shown in the following figure computes the sum bit S and the carry bit C from the bits X and Y. Okay, so we have the sum bit is this expression, X plus Y times xy bar. So we have x plus y comes from this gate. So this, in this circuit, we use the branching method. The input x and y come to this gate and also comes to this gate. Okay, the same input, we use the branching method. Okay, so this, in this gate, it outputs x plus y, goes to this gate, combined with xy bar goes to inverter. So we have xy complement goes to this one. So it is the sum. Okay, the sum bit. And another one, another output, this one is the first output. The second output is C, which is the carry bit. So the carry bit is xy. Okay, xy. So this is the carry bit. You need to use, again, branching. Just use straight line because you need to, no need to pass through any line. So just use straight line to this arrow. Don't forget to draw this arrow as well to indicate these two are the output. The first output is the sum bit. The second output is the carry bit. Okay, the second output is the carry bit. So that's the adder, the half adder, because we don't consider any carry from the previous addition. We just simply directly use this uh, produce this circuit without considering any adder from previous addition. So this is the half adder circuit. Okay, we use the full adder to compute the sum bit and the carry bit when two bits and a carry are added. That means other than xy, previously we have only xy, we also have another input which is c. So this C comes from other addition, from other circuit. Okay, so it goes to our circuit. So our circuit for full adder, we have X and Y, which are the original input, and we have additional input, which is C, comes from the previous addition. So we call this kind of circuit as full adder. We use the full adder to compute the sum bit and the carry bit when two bits and carry bit are added. The inputs to the full adder are the bits xy and the carry ci. That means it can be more than one carry bits. The output of the sum bit s and the new carry bit. So the output for the full adder, it produces our sum bit, which is the original output. So another one is the carry bit. Again, carry bit. Because the previously it is ci, so the new one is ci plus 1. The input and outputs for the full adder shown in table 4. Okay, so this is the table 4. This is our input, original input, previously x and y. So now we have additional one, which is ci. So we need to come out with all this combination, unique combination for three inputs, 1, 1, 1 until 0, 0, 0. And for s, we have this value for s, which is the sum bit. Okay, and this one is the carry bit, which is another output, new output, which is carry bit. Previously we have ci, so for this one we have ci plus 1, means it is a new carry bit. The two outputs of the full adder, the sum bit s and the carry ci plus 1, are given by the sum of products expansion. Okay, so in order to come out with this, the expression for s and also the expression for the carry, we need to use the previous methods. Okay. In order to come up with the expression, we need to use the sum of product in order to come out with the expressions. Okay, so no need to show here. Just use the previous method to come out with which one is the sum. Okay, again we consider the one outputs and then come out with the expression. So same goes with the carry. We also consider the one values and come out with the expression. Okay, so however, instead of designing the full adder from scratch, half adders are used to produce the desired outputs. Okay, so this is the full adder circuit using half adders is shown in the following figure. Okay, so in this full adder, okay, this is full adder circuit. So we have ci comes from previous calculation. Okay, this is the original inputs. So we can use the existing half adder, just put it here, okay, to combine together with other Boolean operators, and finally we can come out with the full adder, okay, to represent the full output for the given table. Okay, this is the first output, okay, which is the sum bit, and this is another output, which is the carry bit, new carry bit. The previously it is ci, so for the new carry bit it is ci plus 1. So finally, the following figure shows how full and half adders can be used to add the 3 bits integer. Okay, 3 bits integer, this is the first integer and this is the second integer, to produce this integer sum, the sum of these two integers. Alright, so again, because this is adder, so we have new carry output, new carry output. Note that S3 is the highest, has the highest order bit in the sum is given by carry C2. This is the highest one, it is given by the carry, the new carry bit. Alright, so I think that's all for in this chapter. So thank you class.